Welcome! In this session, we'll explore LeetCode problem number 923, threesome with multiplicity. This is an interesting problem where we count unique triplets that sum to a target value, with specific constraints. Let's dive in to understand the problem and its solution step by step. In this problem, we are tasked with finding the number of unique tuples, I, j, k, from an input array, RR, such that the indices satisfy the condition I less than j less than k, and the sum of the elements at those indices equals the given target. Since the number of such tuples can be very large, the result must be returned modulo 10 to the power of 9 plus 7. The input consists of an array of integers, where the length of the array is between 1 and 3000, and each element lies in the range 0 to 100. The target itself is an integer between 0 and 300. The output is a single integer representing the total count of valid tuples. Now let's look at an example to clarify how such tuples are identified. Consider the input array ARR equals 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and the target 8. The output for this input is 20. To understand why, we need to examine all the tuples that satisfy the conditions. For example, we can take the values 1, 3, 4, with indices 0, 4, 6. This tuple sums up to 8, and the indices satisfy I less than j less than k. Similarly, swapping the positions of the 3 and 4 in the indices generates permutations of this tuple. There are several more combinations, such as 2, 3, 3, or 2, 3, 4, and when we account for all valid permutations, we end up with a total of 20 tuples. This demonstrates the importance of considering both the values and their respective indices within the array. Now let's look at another example. Suppose the input array is ARR equals 1, 1, 2, 2, 2, 2, and the target is 5. The output in this case is 12. Here, one of the tuples that works is 1, 2, 2, with indices 0, 2, 3, and swapping the positions of the second and third elements in the indices gives additional permutations. Similarly, 1, 2, 2, with indices 0, 2, 4, or 0, 2, 5, also contribute valid tuples. By systematically exploring all such combinations while respecting the condition I less than j less than k, we find that there are exactly 12 valid tuples in total that meet the criteria. To continue, the remaining permutations of 1, 2, 2 include indices 1, 2, 3, 1, 2, 4, and 1, 2, 5. Each of these satisfies the required conditions, contributing to the total count of 12 tuples. This example illustrates how repeated values in the array, like the multiple 2s in this case, can result in a variety of valid permutations. Now turning to the constraints, the array length is at most 3000, and the values in the array are between 0 and 100. The target sum is between 0 and 300. These constraints ensure that the problem is computationally feasible while still requiring an efficient approach for larger inputs. Finally, let's discuss some edge cases and considerations. First, if the input array has only 3 elements, and their sum does not match the target, the result will simply be 0. For example, with ARR equals 1, 2, 3, and target equals 10, there are no valid tuples. Another case is when all elements in the array are the same, and the target is a multiple of that element. For instance, in ARR equals 2, 2, 2, 2, 2, with target equals 6, the solution must account for all valid combinations, which in this case is 10. For large inputs, where the array length approaches 3000 and values are close to their maximum, the algorithm must remain efficient. Lastly, the modulo operation ensures that the result does not exceed 10 to the power of 9 plus 7, which is especially important for cases with a high number of tuples. Ensuring correctness and efficiency even in these scenarios is key to solving this problem successfully. To solve the problem of counting unique tuples, I, j, k, such that I is less than j is less than k, and their sum equals the target, we need to carefully consider the constraints. The array can be quite large, so efficiency is crucial. A straightforward approach would be the brute force method, where we iterate through all combinations of 3 distinct elements using 3 nested loops and check if their sum matches the target. However, this method has a time complexity of n cubed, which becomes computationally expensive for large arrays, especially when the size can go up to 3000. This inefficiency makes the brute force approach impractical for this problem, as it would take too long to compute results for larger inputs. Thus, we need a smarter, more optimized strategy to tackle this challenge effectively. A more efficient solution involves using a frequency map to count occurrences of each number in the array. This approach reduces redundant calculations by allowing us to directly determine how many valid tuples can be formed with specific values. The process begins by building a frequency map where each key represents a number in the array, and its value indicates how often that number appears. Then, for every combination of two numbers, x and y, we calculate the third number, z, as target minus x minus y. We check if z exists in the frequency map and satisfies the condition x is less than or equal to y, which is less than or equal to z. Depending on the relationship between x, y, and z, we use combinatorics to count the valid tuples. For instance, if all three numbers are distinct, we multiply their frequencies. If two numbers are the same, such as x equals y but not z, we calculate combinations using the formula for choosing 2 out of the frequency of x and then multiply by the frequency of z. If all three numbers are the same, we calculate combinations of 3 from the frequency of x. Finally, we sum all valid counts and return the result modulo 10 to the power of 9 plus 7. This method has a time complexity of n squared, due to iterating through pairs and constant time hash map lookups, and it also uses n space for the frequency map. This balance of efficiency and correctness makes it a strong candidate for solving the problem. An alternative strategy involves sorting the array and using the two-pointer technique to identify valid triplets. After sorting, we iterate through the array, and for each element, we use 2 pointers, one starting just after the current element and the other at the end of the array. The idea is to adjust these pointers based on the sum of the current triplet, moving them inward to find combinations that match the target. This method has a time complexity of n log n, for sorting and n squared, for iterating and adjusting the 2 pointers, with a space complexity of 1. While efficient, this approach has some drawbacks. Managing duplicates becomes more complex, as additional logic is needed to avoid overcounting the same triplets. This makes the two-pointer technique less intuitive and slightly more cumbersome compared to the frequency map method, which inherently handles duplicates more naturally. Therefore, while effective, this approach is not the most suitable choice for this particular problem. The optimized approach using a frequency map was selected as the best strategy due to its balance of efficiency, clarity, and simplicity. By leveraging a frequency map, we avoid redundant computations and directly calculate valid combinations using combinatorics. This method naturally handles duplicate values without requiring additional logic, making it more elegant than the two-pointer technique. Furthermore, it eliminates the need for sorting the array, which simplifies the implementation. With an n squared time complexity and an n space complexity, this approach performs well within the problem's constraints. Ultimately, the frequency map approach stands out as the ideal solution, offering a clear, robust, and efficient way to count the valid tuples while adhering to the constraints of the problem. In this problem, the objective is to determine the number of unique tuples, I, j, k, where I less than j less than k, such that the sum of the elements at these indices equals the given target. Since the array may include duplicates, we need to account for the multiplicity of elements when counting valid combinations. To tackle this efficiently, we start by pre-computing the frequency of each unique element in the array. This helps us group duplicate values together, minimizing redundant computations. Using a dictionary or Python's collections accounter, we can map each unique number to its count for constant time lookups. For example, if the array is 1, 1, 2, 2, 3, 3, 4, the frequency dictionary becomes 1, 2, 2, 2, 3, 2, 4, 1. Next, instead of iterating over all possible index triples, we generate combinations of unique numbers from the frequency dictionary. This drastically reduces the search space, as we only examine unique values rather than every index in the input array. To efficiently generate combinations, we use nested loops to iterate over all unique numbers from the frequency dictionary. Let's call the numbers x, y, and z, where x less than or equal to y less than or equal to z. For each combination, we check if their sum equals the target. The key here is to focus only on combinations of unique numbers, as this avoids the inefficiency of iterating through all triplets in the original array. Once we identify a valid combination, we need to handle the multiplicity of these numbers. Depending on the relationship between x, y, and z, we calculate the number of valid tuples using combinatorics. If all three numbers are the same, the formula frequency x asterisk frequency x1 asterisk frequency x2/6 gives the count of tuples. If two numbers match, for example x == y less than z, we compute frequency x asterisk frequency x1/2 asterisk frequency z. And if all three numbers are distinct, we simply multiply their frequencies together, frequency x asterisk frequency y asterisk frequency z. These formulas ensure that we account for all possible tuples while avoiding double counting. To implement the combinatorics, we handle each case explicitly in code. If x, y, and z are all the same, we calculate the count of tuples using the formula frequency x asterisk frequency x1 asterisk frequency x2/6. If x and y are the same but less than z, we use frequency x asterisk frequency x1/2 asterisk frequency z. Similarly, if x is less than y and y equals z, we compute frequency x asterisk frequency y asterisk frequency y1/2. Finally, if x, y, and z are all distinct, the count is simply frequency x asterisk frequency y asterisk frequency z. By iterating through these conditions, we ensure that every valid combination of x, y, and z is considered. After processing all combinations, we return the total count, modulo 10 to the power of 9 plus 7, as required by the problem constraints. This ensures that our result stays within the specified limits, even when the input array is large or contains numbers with high frequencies. This algorithm is efficient because it reduces the search space significantly. Instead of examining all possible O and cubed combinations of indices in the array, we only consider O, U cubed combinations, where U is the number of unique elements in the array. Since array values are bounded between 0 and 100, U is at most 101, making this approach much faster than directly iterating through the input. Using combinatorics to handle multiplicity ensures that repeated numbers are correctly accounted for without introducing unnecessary complexity. Additionally, modulo arithmetic is used to keep the results manageable, preventing overflow when working with large inputs. The algorithm also gracefully handles edge cases, such as when all elements in the array are the same, when no tuples satisfy the condition, or when the array is extremely large. For instance, in an array like 2, 2, 2, 2, with a target of 6, the approach correctly calculates the number of valid tuples. Similarly, if no valid tuples exist, the algorithm efficiently returns 0. Let's analyze the complexity of the algorithm. The time complexity is O, U cubed, where U is the number of unique elements in the array. Since U is at most 101, this is effectively a constant time operation relative to the size of the input array. The space complexity is O, U, because we store the frequency of each unique number in the frequency dictionary. With these optimizations, the algorithm is both time efficient and memory efficient. Finally, the implementation combines all the steps we've discussed. After pre-computing the frequency dictionary, we iterate through all pairs of unique numbers, calculate the third number z, and count valid tuples using our combinatorics formulas. The total count is then returned modulo 10 to the power of 9 plus 7 to meet the problem's constraints. This structure ensures clarity and correctness while leveraging Python's built-in tools like collections, counter for simplicity. Finally, the function returns the count modulo 10 to the power of 9 plus 7. This ensures that the result adheres to the constraints of the problem, even when the input array is large or contains high-frequency elements. By systematically combining frequency calculations, combinatorics, and modulo arithmetic, the algorithm efficiently solves the problem while maintaining clarity and correctness. This concludes the implementation of the solution for three-sum with multiplicity. Here, we start by importing the counter class from the collections module to efficiently count the frequency of elements in the input array. Inside the solution class, we define the function threesummulti, which takes the array ARR and the target value as inputs. To handle large results, we set a constant mod to 10 to the power of 9 plus 7, which will be used later to return the result modulo this value. Next, we create a counter object to count the occurrences of each number in the array and extract the sorted keys from this counter, which represent the unique numbers in ascending order. We also initialize the result variable to 0, which will store the final count of valid triplets. Now, the logic begins with a nested loop to iterate over the unique keys. For each pair of numbers, x and y, we calculate z, the third number required to meet the target sum. If z is less than y, we break out of the inner loop since any further combinations will not satisfy the condition due to the sorted order. If z is not in the counter, we skip to the next iteration. Next, we handle 4 cases based on the relationships between x, y, and z. If all 3 numbers are the same, we calculate the number of combinations using the formula for selecting 3 items out of count x and add it to the result. When x and y are the same but different from z, we calculate combinations of x and multiply by the count of z. Similarly, when y and z are the same but different from x, we calculate combinations of y and multiply by the count of x. Finally, if all 3 numbers are different, we multiply their counts and add the result to the total. This structure ensures we accurately count all valid triplets based on their frequency in the array. After processing all possible combinations of x, y, and z, the function concludes by returning the result modulo mod. This ensures the result remains within the constraints of the problem, avoiding overflow and meeting the requirements for large outputs. By breaking the problem into clear cases based on the relationships between the numbers, the implementation efficiently calculates the total number of valid triplets while leveraging the counter for fast lookups and frequency calculations. Here, we start by importing the necessary libraries and defining the 3sum multi method, which takes an integer array ARR and a target sum as inputs. We declare a constant mod to handle the modulo operation, ensuring our results remain within bounds for very large numbers. Next, we create a hash map named count to store the frequency of each number in the array. By iterating through the array with a for each loop, we populate this map, where the key is the number and the value is its count. We then extract all unique keys from the count map and sort them. This allows us to work efficiently with combinations of numbers. A variable result is initialized to store the final count of valid triplets. Now, we use 2 nested loops with indices I and j to iterate over pairs of numbers, x and y, from the sorted keys. For every pair, we calculate the third number z needed to reach the target by subtracting the sum of x and y from target. If z is smaller than y, we break out of the inner loop, as further combinations would not work in sorted order. Additionally, if z is not present in the count map, we skip to the next iteration, as it means there's no valid triplet with the current x and y. Once we confirm that z exists in the count map, we proceed to calculate the number of valid triplets based on the relationship between x, y, and z. If all 3 numbers are the same, meaning x equals y equals z, we use the formula for combinations to count triplets, dividing the product of count x1, and count x2 by 6. If only x and y are the same and different from z, we calculate combinations for x and y, then multiply by the count of z. Similarly, if y and z are the same but different from x, we calculate combinations for y and z, then multiply by the count of x. Finally, if all 3 numbers are distinct, we simply multiply their respective counts. Each case adds its result to the result variable. After processing all valid triplets, we return the result modulo mod to ensure it fits within the required bounds. This implementation is efficient due to the use of frequency counting, sorting, and targeted iterations, making it suitable even for larger inputs. Here, we are starting with a basic example where the input array is 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and the target is 8. The first step is to initialize our variables. We define mod as 10*** 9 plus 7 to ensure our result stays within bounds for large inputs. Next, we use the counter class to count the frequency of each number in the array. This gives us 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, meaning each number appears exactly twice. We then sort the unique keys from the counter, resulting in 1, 2, 3, 4, 5. Finally, we initialize result to 0, which will store our total count of valid triplets. With these variables set up, we are ready to start iterating through potential triplets. Now, we begin iterating through the possible triplets using nested loops. The outer loop iterates over indices I and values x from the sorted unique keys. For I equals 0 and x equals 1, the inner loop iterates over indices j and values y. When j equals 0 and y equals 1, we calculate z as 8, 1, 1 equals 6. Since z is greater than y but not present in the count, we skip this triplet. For j equals 1 and y equals 2, z is 8, 1, 2 equals 5. Here, z is valid because it is greater than y and exists in count. Since all three numbers are different, we add count 1 asterisk count 2 asterisk count 5 is equal to 2 times 2 times 2 equals 8 to result. Similarly, for j equals 2 and y equals 3, z is 8, 1 and 3 equals 4, and we add count 1 asterisk count 3 asterisk count 4 is equal to 2 times 2 times 2 equals 8 to result. Next, when I equals 1 and x equals 2, we process the combinations for y equals 2 and y equals 3. For y equals 2, z is 4, and since two of the values are the same, we add combinations using the formula for duplicates, resulting in 2. Similarly, for y equals 3, z is 3, and we add another 2 to result. After processing all pairs, the total result becomes 20, and we return the result modulo mod, which is still 20. In this example, we consider an edge case where all elements in the array are equal. The input array is 2, 2, 2, 2, with a target of 6. We start by initializing our variables. Using counter, we find that all elements are 2, giving us 2, 4. The sorted keys are 2, and result is initialized to 0. Now, we process the triplets. For I equals 0 and x equals 2, the inner loop also selects y equals 2. Here, z is calculated as 6, 2, 2 equals 2. Since all three values are identical, x equals y equals z, we use the combination formula for selecting three identical elements. This formula gives us count 2 asterisk count 2 1 asterisk count 2 2 / 6 is equal to 4 asterisk 3 by 2 / 6 equals 4. Adding this value to result gives a total result of 4. We then return result %mod, which is 4. In this example, we look at a case where no valid triplets exist. The input array is 1, 2, 3, 4, 5, with a target of 20. After initializing the variables, we find the counts of each number as 1, 1, 2, 1, 3, 1, 4, 1, 5, 1. The sorted keys are 1, 2, 3, 4, 5, and result is set to 0. As we iterate through the keys, for any combination of x, y, and z, the calculated z equals target x, y is always greater than the largest number in the array. Since no valid triplets can satisfy the condition, the total result remains 0. Finally, we return result %mod, which is also 0. To recap, in this scenario with no valid triplets, all possible combinations of x, y, and z fail the condition where z must be greater than or equal to y and exist in the array. As a result, the total result is 0, which we return after taking modulo mod. This demonstrates how the solution handles cases with no valid triplets efficiently, ensuring correctness even in edge cases like this. The time complexity of our solution is derived from analyzing the loops and the operations within them. First, the outer loop iterates over the unique elements in the array, which we store in the variable keys. The number of unique elements, denoted as k, determines the number of iterations for this loop, making its complexity O, k. Next, the inner loop iterates over all pairs of unique elements, where the second index starts at the current position of the first. This results in approximately k asterisk, k plus 1, / 2 iterations in total, which simplifies to O, k squared. For each pair, operations such as determining the third element z and checking its existence in the frequency counter are constant time, or O, 1. This includes the arithmetic checks for cases like x equals y equals z or x equals y equals z, which are also O, 1. Therefore, the operations inside the loop do not add additional complexity beyond the O, k squared, contributed by the nested loops. When we combine the analysis, the overall time complexity of the solution becomes O, k squared, where k is the number of unique elements. Now, let's relate this to the size of the input array, n. In the worst-case scenario, where all elements in the array are unique, k equals n, resulting in a time complexity of O, n squared. Conversely, in the best-case scenario, where all elements in the array are the same, k equals 1, and the complexity reduces to O(1). Thus, the overall time complexity is O min n squared k squared, since the number of unique elements, k, directly impacts the number of iterations performed by the nested loops. The space complexity of our solution is determined by the memory usage of the data structures involved. First, the counter object, which stores the frequency of each unique element in the array, requires O(k) space, where k is the number of unique elements. Similarly, the keys list, which holds these unique elements in sorted order, also consumes O(k) space. Additionally, variables like x, y, z, and result only require a constant amount of space, or O(1). Therefore, the total space complexity is dominated by the storage for the counter and keys, making it O(k), where k is the number of unique elements. To put this into perspective, let's compare the optimized approach to a naive or brute force solution. A naive method would involve iterating over all possible triplets, I, j, k, in the array, resulting in a time complexity of O(n cubed). This approach quickly becomes infeasible for larger arrays due to its high computational cost. In contrast, the optimized solution reduces this complexity by leveraging the counter object to avoid redundant computations. Instead of examining all possible triplets, it focuses only on unique pairs of elements and counts valid triplets directly, bringing the complexity down to O(k squared). This improvement is particularly significant when the number of unique elements, k, is much smaller than the total number of elements, n. When analyzing the best, average, and worst-case scenarios, we see how the distribution of elements in the array affects the time complexity. In the best case, where all elements are the same, k equals 1, and the time complexity becomes O(1), as there's only one unique triplet to evaluate. In the average case, the number of unique elements, k, is smaller than n but not minimal. Here, the time complexity is O(k squared), where k depends on the distribution of elements. In the worst case, where all elements are unique, k equals n, and the time complexity increases to O(n squared). Mathematically, the nested loops iterate over all unique pairs of elements in keys, with the total number of iterations bounded by k asterisk, k plus 1/2, simplifying to O(k squared). Since the operations within the loops are O(1), the overall complexity is dominated by this term. On the space side, the counter and keys structures require O(k) space, which aligns with the time complexity's dependence on k. In this section, we'll cover some common mistakes and how to avoid them when solving the threesome with multiplicity problem. First, not accounting for duplicates is a frequent pitfall. When analyzing the array, failing to handle duplicate elements can lead to overcounting the same tuple multiple times, which violates the requirement for unique tuples. To address this, a frequency map, such as Python's collections accounter, can be used to track occurrences efficiently. Next, using a naive triple nested loop to check all possible combinations of three elements is another mistake. This approach has a time complexity of O(n cubed), which becomes impractical for larger inputs. Instead, optimized methods like the two-pointer technique or hashmap-based solutions can reduce the complexity to O(n squared), making the solution much more scalable. Another issue arises from incorrectly managing the indices I, j, and k. Since the problem requires I less than j less than k, neglecting this constraint can lead to invalid tuples. Ensuring this order through the iteration logic is essential. Lastly, in languages like Java or C++, there's a risk of overflow when dealing with very large sums. To avoid this, modular arithmetic, such as taking results modulo 10 to the power of 9 plus 7, is necessary to ensure correctness and prevent overflow errors. Off by one errors are another common issue to watch out for in this problem. These errors occur when array boundaries are mismanaged during two-pointer traversal or when performing hashmap calculations. For example, pointers might go out of bounds or miss valid tuples entirely if boundary conditions aren't properly handled. To fix this, it's important to carefully initialize and update pointers while verifying all boundary conditions. Now, let's discuss some insights that can be useful during interviews. The threesome with multiplicity problem is an extension of the classic threesome problem, but with an added complexity of handling multiplicity constraints. Instead of working with simple arrays, frequency maps are a powerful tool that allow for combinatorial counting of tuples, making the solution more efficient. For sorted arrays, the two-pointer approach is a critical optimization to master, as it significantly reduces the computational overhead. It's also important to discuss edge cases during interviews, such as when all the elements in the array are identical or when the array has fewer than 3 elements. Finally, if the problem involves large sums, be ready to explain why modulo operations are necessary and demonstrate how to implement them correctly. The concepts in this problem are closely related to other problems on LeetCode, and understanding these relationships can help you build a stronger foundation. For example, the three-sum problem, LeetCode number 15, is a foundational problem where you find unique triplets that sum up to 0. It provides the groundwork for variations like three-sum with multiplicity. Similarly, the four-sum problem, LeetCode number 18, extends the concept to quadruplets, requiring additional thought on how to manage larger combinations. The two-sum problem, LeetCode number 1, is a simpler version that focuses on pairs and introduces the idea of using hash maps for efficient lookups. Lastly, subarray sum equals k, LeetCode number 560, is another related problem where hash maps are used to count subarrays that meet specific constraints. Studying these problems can help you recognize patterns and transferable techniques, such as the use of frequency maps and pointer-based approaches, which are key to solving variations of the three-sum problem efficiently. When tackling three-sum with multiplicity, there are several approaches to consider, each with its own trade-offs. The brute force method, with a time complexity of n cubed, involves iterating over all possible triplets. While this approach is straightforward to implement, it becomes computationally expensive for large arrays and is generally impractical. A more efficient method is the two-pointer approach combined with sorting, which reduces the complexity to n squared. By sorting the array and using two pointers to find valid combinations, this method is faster but does require additional space for sorting, which is n log n. Another effective approach is using a frequency map with combinatorics. By storing the count of each element in a hash map, you can calculate combinations efficiently, such as n choose 2. This avoids the need for sorting but requires careful handling of counts and modular arithmetic to ensure correctness. For advanced variations, dynamic programming can sometimes be applied to count subsets that satisfy the required conditions. However, this approach often has higher complexity and is not as practical for standard three-sum problems. Each of these methods has its strengths and weaknesses, so choosing the right approach depends on the specific constraints and requirements of the problem. Great job! We've covered the solution to three-sum with multiplicity, discussed the key concepts, and explored the optimized approach. Remember to practice similar problems to strengthen your skills. Thanks for tuning in, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!